Intro music. Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is the AAS Journal Author Series. And today I'm very happy to have Jameel-Un Nabi with us today. Hi, Jameel.
Hi, Frank. How are you? Thank you very much for having me here.
Oh, it's really great of you to come on and talk about this really lovely APJ paper we'll get to in a little bit. So I'm doing well. It's my Tuesday, May 18th. I'm here in Phoenix. Summer is right around the corner. We hit about 35 C today. We'll probably in another week or two, the power switch will go on. We'll probably get up to 40 C or so. And so what is your geolocation? Where are you at?
Right. Thank you very much. And I am here in Pakistan.
Yeah.
And it's Wednesday morning here, 8:49. So a very good morning to you from Pakistan.
Thank you.
And this primarily is a province called Punjab, and the area location is Wah. So it's a Wah cantonment. It's University of Wah here. I'm in my office. Thank you very much for having me.
Very cool. Very cool. So is summer hitting there yet? Is it nice and toasty? Is it summer? Has the temperature turned on yet there?
Yeah. I'm sorry, Frank. Once again, I lost your voice. So can you please repeat the question again? I'm sorry.
Sure. So you're still in the Northern Hemisphere there. So is it summer yet in Pakistan?
Yes, summer is on here, and it's in full swing. I must say that temperatures are soaring. And only yesterday, in Karachi, we had temperature around 43, 45 Celsius. But here, where I'm speaking from, it's much milder. I would say around 35, 36 is the maximum we go.
Mm-hmm. Yeah, I like 35. It's quite comfortable for me, so it's good. So Jameel, what do you like to do for research?
Yes, I started my career, as an experimentalist when I was doing my master's. But then later on, I found out that that's not my ball game, and I switched later to theoretical physics. And I did my PhD from Heidelberg University in Germany. And then, I got to know quite a good professors there who really inspired me, motivated me, and then I did my PhD in nuclear physics there. Gradually I shifted my interest more to nuclear astrophysics.
Okay.
And so I'm primarily interested in evolution of stars, and particularly how they would end up their life. So, supernova explosions, associated phenomena I'm interested in from a theoretical point of view, and that's what I like to do.
Cool. And that is going to bring us to this very lovely APJ article on investigation of important weak interaction nuclei in presupernova evolution. And Jameel, take us away.
Right. Thank you, Frank. Thank you once again for giving me a chance to go through this this very nice paper. I would like to start by saying that this is not the a pioneering paper, and my predecessors and other people have done similar calculations in the past. But there are a couple of things that are unique to my calculation, which I would highlight, very soon. Precisely, people who are doing these simulations of core collapse supernova, they would find it challenging to come up with an explosion. A lot of physics would go into these big, huge codes, and people would be doing different type of calculations. They call it 1D, 2D, and 3D calculations. One of the very important inputs would be the nuclear physics input for these type of simulation codes.
Yep.
And this is precisely where I come in. And they would normally have thousands of nuclei in these type of scenario. The temperatures and the density is very high. So if you talk about the temperatures in gigakelvins, that is 10 to the power 9 kelvins. So it would be, of that order. And then the densities also would be, going up as high as 10 to the power 11, 12 gram per centimeters cube.
Yep.
So high density, high temperature environment, and then a lot of nuclei, and then you have to come up with the weak interaction rates, primarily the beta decays and the electron capture. And the reason for this is that the stability of the star, is depending primarily on two forces which balance each other. So, the gravitational force, of course, would try to, put it downwards into the center, and then it is balanced by a degeneracy pressure supported by the electrons. And, once these electrons starts getting captured, the degeneracy pressure would go down, and then, the collapse would stop. So the weak interaction rates in that respect is very important. So people have done these calculations in the past, beta decays, electron captures in high temperature density environment. That's nothing new. But then not only this, but also their respective abundance is important. I mean to say you have to have a sizable number of nuclei for them to get, come up with these type of calculations. So, when you have a product of these type of the abundance and the weak rates, then, one important parameter would be the lepton fraction for the stellar matter, which is primarily the ratio of the electron to the baryons in that particular scenario, in that stellar matter. And the rate of change of that parameter, that is very important for the modeling of this type of phenomena. So in order to get this rate of change of the lepton parameter, this paper is all about that. And then those nuclei which would really influence this parameter the most would be most important in this scenario. Yes. And so in the past, so I started with a bigger pool of 728 nuclei. And, then the calculation of the mass abundance is primarily based on, assumption of the nucleostatistical equilibrium. And we just have a very simple Saha equation to solve, and we come up with the abundance. But then again, something new in my calculation, and people have done this in the past as well. So what is new about my calculation is that when I did this mass abundance calculation, I, the nuclear partition functions that would plug in the Saha equation, okay. They normally are more precise and reliable if you have performed a summation on the discrete energy levels rather than an integration over some, continuous ranges of energies. Okay. So up to 10 MeVs, I did perform a summation on discrete energy levels. And these discrete energy levels play a very important role in the stellar scenario. Fuller, Fowler, and Newman, way back in 1980, they pointed this out that, in the intermediate temperature density range, the discrete level, the transitions between them play a very important role. So what is desirable was to have a discrete states. So I had that up to 10 MeVs, but beyond that, of course, I also used a simple Fermi gas model and, performed the integration to come up with the partition functions. So that is a new thing that we took discrete states up to 10 MeV. And then, which resulted, of course, in my abundance, the nuclear abundance that I got was on the average, up to 4 orders of magnitude smaller than my previous calculations. Oh, wow. So that was some change there. And then the weak rates also was microscopic in nature. By microscopic, I mean I performed a state-to-state from parent to daughter partial rates for electron capture and beta decays. Okay. Previous calculations would be using some approximations which they call as the Brink axle hypothesis. They would approximate the excited state Gamow-Taylor stem distributions. I'm sorry, these terms are a little bit technical terms, but I'm sure people in my field would know what these Gamow-Taylor transitions are. Primarily, they are the charge changing transitions transforming a proton, to an electron, and this vice versa. So these gamma-Taylor transitions from the parent ground state is very easy to calculate, but then from excited states, it's a challenging issue.
Yes.
And then normally the people would come with these type of approximations, but then in my model, I performed state to state this type of weak interaction calculations.
Cool.
And then, I came up with a list of, in this paper, can I scroll it down, or
Sure.
is it possible to go down to the tables
tell me,
a little bit?
Tell me where to go. So let's go ahead.
Can you just go to table 1, because there I would be showing you some of the abundance calculations in table 1.
Okay.
Yeah. So yes, primarily these are, you would see here the electron capture rates here, and this is my calculation, and this is the calculations performed using the independent particle model, first used by Fuller, Fowler, and Newman, and then later used by Obderheide and collaborators. It's a very famous pioneering paper in 1994. So I'm comparing that with this independent particle model calculation, and a more recent one by the Gross theory is here. But then, the problem with this is they are only taking the ground state transitions into considerations. So you would notice the numbers are quite small here compared to the other numbers. Here we also take the excited states in the PNQRP and the IPM. Right. So you would really see the orders of magnitude difference between the rates. This is what is important. I mentioned earlier on, rate of change of the lepton fraction. And again, this is the comparison there. And you would see that, I'm a little bit smaller than the independent particle model at times. And at times, I'm also bigger, but then there are some fine tuning of the problems there. So if you scroll down, we have similar tables for, for different conditions, electron captures as well as beta decay. If you go down to table 2 and 3, just, scanning through them.
We're at table 2 right now.
Yes, so table 2 is a similar one, but then the conditions have changed. So you see the important parameters would be the stellar densities and the temperatures. T9 is in 10 to the power 9 kelvins. This is 10 to the power 8 gram per centimeters cube. And then the lepton fraction is going from now it's 0.45. And if you scroll down to table 3, so you will just see that the conditions would change there a little bit more. Can we go to table 3?
Yes. So we're on table 3.
Yeah. So now you see, you would notice that the lepton YE is now going up. Now it's 0.47. The temperature is a little bit coming down, the densities. And so, these are the typical snapshots, I would say, of the star at that particular time. And I'm just comparing my calculated numbers with the previous calculations. These were for electron capture. And in the subsequent tables, if you go down to table 4, you would see that I would now, can we have table 4?
Yeah. We just have a little bandwidth lag, that's all. We're at table 4 right now.
Yeah, there is a little bit of time lag here, I think so. Yeah. So now, same tables, same conditions, but then now for beta decay. The previous 3 was for electron capture. And these are for beta decays. Okay. So try to understand that the electron capture would have a negative effect, because they will remove the electrons. So it will reduce that fraction, lepton to baryon, and the beta decays had the reverse, effect. So again, the same conditions, I would start with a small YE value of 0.42 and then increase this up to 4.47 or something like that. And I will compare primarily 2 things here. One is my weak interaction rates with the previous models. And the second one would be the rate of change of the lepton fraction. So 5, 6 would be the similar tables like 1, 2, 3. Table 7 is something which I would like to really discuss rather in detail, because that really would be a good summary of this paper. And so this list, for example, is a new list, a very new list, which should be, the core collapse simulators should take note of this list. And there are some good features in this list. For example, there are some new entrants which were not present in the previous list that we had. And why they are in here now, I told you in the beginning that this calculation has a better description of the nuclear partition functions, number one. Number two, a bigger ensemble of like 700 plus nuclei. Number three, macroscopic calculations of peak interaction rates. So I believe this is a very good combination, and the end result should be more reliable. And of course, we were expecting some new entrants in the list. So the nuclei with the sterics, you can see in my table, this is just a list of top 50. By the way, I can go on to top 700.
Yes.
But then we don't need so much of the nuclei. So top 50 should suffice. And we have some new entrants there. So this is something important to take note. Roughly 10% new entrants were there for electron capture list, and roughly 30% new entries were there for the beta decay nuclei in my calculation. This is a take-home message, that we have some new nuclei in these lists, and it's worth checking them. For the core collapse simulators should take note, see what difference it might make in their calculation. Another important aspect of this, so I should also explain this ranking parameter here. This is something which people might ask, what is this? This is the same parameter which Abdur and collaborators took way back in 1994. So what they do is they would change this parameter, the lepton fraction parameter, to 0.4 to 0.5. This is a very important range. Why? Because in this particular range, I would show later on in my graph that there is a very tough competition going on between the capture and the beta decay rates. And also in this range, you would see that the beta decays would surpass the electron capture. I will show that later on. But then it's precisely somewhere here, where things really goes, and people are really focusing on in this range. So in this particular range, when the YE fraction changes from 0.4 to 0.5, which nuclei would have the greatest effect, the biggest effect, I mean to say, in changing that parameter with respect to time. So that is how we get this this ranking parameter, which I'm showing you in this column. So it's sort of an average. And according to my calculation, 56 manganese, as far as electron capture nuclei are concerned, would have the biggest contribution in changing this YE parameter. So, and then so on, 57, 52 vanadium, and so on and so forth. For the beta decay nuclei, the most important would be 67 nickel. The second entry is, by the way, a very new entry, which was not present at all, 49 scandium in the beta decay case. So this is very important, that the second most important in my calculation is a new entry. So these are the ranking parameters, and they are defined in my paper. I think it's in equation 18 of the paper, where I do define these ranking parameters. This list is important for the core collapse simulators. And if you scroll down to the last figure of the paper, I think it's figure 6. Can you go down to that, Frank, please?
Yes.
Figure 6.
Figure 6. Just waiting for the bandwidth.
Yeah, the last one. Figure 6.
Yes.
Yeah, thank you very much. Now, this is an interesting figure, and you see here I'm comparing with 3 other very important calculations. So this is PNQRPA, that's me, and the blue one. These dashed lines, the black ones, these are the independent particle model calculation performed by Verheiden collaborators. The green ones, this is the growth theory calculations, Ferrari in 2016. And the red ones are the shell model, 2000, Langanke collaborators. So now what this is all about, you see, on the horizontal axis, you would see this, again, this very important parameter, the lepton to barium parameter. And the important range is, as I mentioned before, somewhere between 0.4 and 0.5. And on the vertical axis, it's how it changes with respect to time, right? Per seconds, units of per seconds. So you would see one curve is like a cup-shaped curve, and the one is like a cap-shaped curve. So this one, the cup-shaped curve, you can see in the blue, for example, this would be for the electron capture, and the blue one, in the cap-shaped type of a thing, that would be for the beta decays. Okay. And you would see the green for the red as well. So, you would also see that for the majority part of, cases for YE, electron capture is much bigger contribution than the beta decays. Yes. But in this particular range, somewhere between 0.42 something and 0.47 or 0.46 something, you would see that the beta decays would surpass the electron capture. And this is a very important regime. So you would see, first of all, that the blues and the reds are in very decent agreement, I would say. And it's not a surprise because both the shell model and the QRPA models are primarily macroscopic in nature. So I would be expecting them to be in good agreement with each other. And so they are. You would see that this range, so this is, I think, from something like 0.4 to something, from to 0.46 something, is my range. This is roughly 10% or so bigger than the IPM calculation. Let me just confirm that number, because I want to be very precise what that number is. Yes, this number is like 11%. Bigger than this range I'm talking about. So it's precisely 0.424 to 0.455. This is the range which is given in my paper, which is, of course, is shared by two of the co-authors. I must mention that. It would be very unfair of me. These both are my students. Mr. Asimullah, he is my PhD student, and the other one is Ali Abbas, who was my master's student. So both are, worked with me in this calculation, and I must acknowledge that. Great. So yes, 0.424 to 0.455 is the range which I calculated, where my beta decay rates dominate the competing electron capture rates. And this range is 11% bigger than those proposed by the independent particle model, and at the same time 6% smaller than that range proposed by the growth theory. So these are the two messages, list of new nuclei, top 50, and this new range, which, by the way, is in good agreement with shell model. That is the take-home message from these two papers. I would be happy if you have some more questions, Frank.
Okay. I do, actually. So let's suppose that let's suppose a core collapse person or a pre-supernova person wanted to incorporate these new PNQRPA rates inside of their models. How would they get those rates? Should they just take the three tables for those three YE and interpolate between those three, or is there a database available somewhere where they can get more details?
Yes. Yeah, thank you. I'm sorry, the voice connection is a little bit distorted, but then I probably got your question, I think so. Yes, if you want to have a fine grid, sort of a fine grid where you can interpolate the rates and, These are available online as well.
Okay.
My rates were present there.
Okay.
They are present, yeah.
Okay. Very good. Is that in the paper somewhere, that URL?
Not in this paper, but then, in my original calculation, the website was given when I first published the week rates. They were way back in, 2004, I presume. And it was
Okay.
atomic data and nuclear data tables. And there, the web link is given where I should have put it here. I think so. Yeah, that was.
What we can
I
do
forgot
is
that.
we'll put it in the link below the video. So we'll have it there.
Right. I'll send you that.
Okay, that would be really great. Very cool. Very nice. Let me ask, where do we go from here? Let's say over the next 5 years or so. Do we expand it out to 1,000 nuclei? Are there some experiments that could be done in the lab to verify some of these? Or just sort of where do we go over the next 5 years for the future?
Oh, that's a very interesting question. And with certainty, the way that technology is going ahead, it's very difficult to predict, I mean to say. But then, by leaps and bounds, the technology is growing exponentially. So, you see, I would answer your question on two fronts. First of all, what are the advancements that we expect, on the theoretical and computational side? And then what are the advancements that we expect on the observational side?
There you go.
So the computation power is increasing day by day. Supercomputers and then super duper computers, and these type of calculations. So very good for us. I mean to say, there are so many input parameters and there's so many nuclei. So computing power certainly would help us to come up with a more precise and reliable simulation. I must say that. And people are coming up with some very efficient algorithms, and not only so they started with a symmetric sort of a simulation, what we call as a 1D, and then now we have 2Ds and 3Ds, and they're coming up with more dimensions, multidimensionality. So these type of hydrodynamic simulations, they would be more reliable once the computation power is big. So that is what we expect. At the same time, the nuclear models, they are trying to prove themselves for their prediction power, coming with new parameters. And then the experimental data are coming. I would name FAIR in Germany, RIC in Japan, and then so many other places. They are coming up with these type of NP and PN experiments. They are very important to get some idea of the gamma-molecular strength, which really goes into this type of in scenario. So that is the theoretical part. For observational part, yes, there are so many projects that are coming up in the near future. These space-based telescopes, and some other big projects that are coming up very soon. And I'm sure with new observations, we're observing more these supernovae. There are so many amateur astronomers, that are hooked up with these type of events that are occurring. So we're getting more and more observational data as well, and that is very good for the theoreticians, so that they can test their models. In nutshell, the coming 4 or 5 years, very exciting, and hopefully we would be able to better understand the very complex dynamics of supernova explosion in a better fashion. And just to a reminder for the viewers, that it's also very important because it is connected with the nucleosynthesis problem. I mean to say, more than 50%, these heavy element nucleosynthesis, they are believed to be occurring, in a region nearby the supernovae. So these two are connected intimately. So a better understanding of this can also help us, resolving these nucleosynthesis problems, where we again have some discrepancy between the observed data and the theoretical calculations. Some of the peaks are not matching, especially the third and peaks there. not matching well. So, it's very exciting in nutshell.
Cool. Cool. Very bright future ahead for these calculations and the ramifications. So Jameel, I want to thank you once again for spending some time today and chatting about your really lovely APJ article.
Thank you very much, Frank. I should thank AAS for giving me this opportunity. And I hope that, some of the young researchers would be sooner or later watching this video and, get motivated. And, there was a time when I got motivated myself when I was a young student. And then I hope so I would be able to motivate some young researchers into this field. And thank you very much for having me here. I'm much obliged. Thank you very much.
Thank you. All right, everyone, that'll do. And we'll see you on the next one. Bye-bye.
Bye.